Hi, I'm Anurag Sarkar from Northeastern University, and in this presentation, I will be talking about work done with my co-author Seth Cooper, where we used conditional variational autoencoders for both generating whole levels for platformers and dungeons, as well as taking a step towards blending levels across these two genres. And so, what was the motivation for this work? Well, in recent years, there's been a bunch of research centered around using variational autoencoders, or VAEs, for generating levels, as well as blending levels for a number of different games. And additionally, to add more controllability to these models, conditional VAEs have also been used for level generation and blending. And these are a type of VAE that can be trained using labels, and then generation can be controlled by using these labels to condition the output. So as shown in this image taken from one of our prior works, the labels can, for example, be used to control the content within a generated level segment. Now, these types of models have been shown to work quite well, but they do suffer from a couple of drawbacks that we wanted to address in this work. So, first is that because these models work with fixed size inputs and outputs, and because typically in PCGML we don't have a lot of data to train on, we were forced to train these models on segments of levels. And so, these models typically learn to generate segments that are independent or unrelated to each other, and so additional methods or algorithms have to be applied to figure out how to combine these generated segments into a complete level that makes sense. And second, most, if not all, of the prior blending work has been for platformers, and so we want to take a step towards blending levels taken from games from different genres and not be restricted to the platformer domain. And the key idea of this paper that essentially allowed us to address both of these issues is that unlike prior work where we vary the label when generating using a conditional VAE to vary the content in the generated segment, here we instead use the labels to control the orientation or the direction of progress through a given segment. And as I'll explain in the rest of this talk, doing this enabled us to both generate whole levels for platformers and dungeons, as well as produce levels that blend platformer segments with dungeon rooms. And so, as an overview of the approach, we trained conditional VAEs on levels from Zelda, Mega Man, Metroid, Lode Runner, as well as a bunch of blended models, so covering both dungeons as well as a number of different types of platformers, with all the level data taken from the video game level corpus, or VGLC. And we trained 4 versions of each model with latent sizes of 4, 8, 16, and 32 dimensions. And for our labels, as mentioned in the last slide, we had the labels indicate progression rather than content. So for platformer segments, the labels indicated the directions that were open to allow player movement. For dungeon rooms, the labels indicated the directions that had doors. And so, as you will see, by using specific labels for generation, we can produce segments in rooms with openings and doors in desired directions. And this in turn allows us to connect segments to form platformer levels and rooms to form dungeons, but also connect segments with rooms to produce levels that blend both platformers and dungeons together. So before going over the details of our approach, I want to briefly cover how VAEs and conditional VAEs work. So VAEs are latent variable generative models. They consist of encoder and decoder networks where the encoder learns a mapping from the data to the latent space and the decoder learns the mapping from the latent space to the data. And after training, this learned latent space enables generating new outputs via operations such as sampling and interpolation. And the way that conditional VAEs build on regular VAEs is that during training, each input data instance is associated with a label. And using the example on the slide, the data instance here is the image of the digit, and the label specifies what digit this image represents. And so the input and the label are concatenated together and passed through the encoder to obtain a latent vector. And then the same label is concatenated with the latent vector and passed through the decoder. And an interesting result of this is that the same latent vector could be made to produce different outputs by varying the label during generation. So in the example on the right, we see the same latent encoding is decoded differently based on the provided label. Okay, so coming to our actual method, the main premise that facilitates the use of conditional VAs for this work is that levels in all these games can be seen as composed of sections connected together. So this is perhaps most evident in Zelda, where discrete rooms are connected based on the location of doors to form entire dungeons. but is also true for platformers where you can view the levels as being made up of these discrete segments connected based on the directionality of player movement through them. And so training a conditional VAE on the discrete sections while using labels indicating how they can be connected to each other should yield a model that can generate whole levels composed of these interconnected sections. So for each game, we used binary encoded vectors of length 4 as the labels, with each element corresponding to a direction, with a value of 1 indicating that that direction is open or has a door, and 0 indicating that that direction is closed or doesn't have a door. And just looking at one of these examples, so the Zelda room, as you can see, has doors above, below, and to the left. And so the first three elements of the label are set to 1. There's no door to the right, so the fourth element is set to 0. And for Zelda, we worked with 11 by 16 rooms with labels indicating directions that had doors. For both Metroid and Mega Man, we trained on segments of size 15 by 16 with labels indicating directions that were open that admitted player movement. For Load Runner, we needed a slightly different formulation. So all Load Runner levels have a fixed dimension of 22 by 32 tiles. So a standard VAE is actually quite well suited for generating whole levels, but we still wanted to test this conditional VAE approach. And so we divided each of the whole levels into 4 quadrants of 11 by 16 tiles. And the labels for each of these quadrants were assigned to indicate in which directions that quadrant was connected to another in the original level that it was taken from. So looking at the example on the slide, the label is 0, 1, 1, 0. So in the original level, there was a segment to the left of this segment and below it, but not above it and not to the right of it. Okay, so how do you do blending with these types of labels? Well, we just add a simple extension. So for an n-game blend, all we do is concatenate an n-element binary vector to the 4-element directional vector from the prior slide in order to specify the game that a segment belongs to. So just as a concrete example, suppose you're blending Mega Man and Metroid. So that's a 2-game blend. So for that, we concatenate a label with 2 elements to the 4-element directional label. So as in this example, the label for Mega Man is 0, 1, the label for Metroid is 1, 0. We concatenate those with the directional label to get a final 6-element label for training. And so using this formulation, we train models for 5 different blends, Metroid Mega Man, Zelda with each of the 3 other games, and also a 3-game blend involving Zelda, Mega Man, and Metroid. And more details regarding the model architectures, the hyperparameters, and training conditions can be found in the paper. So moving on to evaluations, we looked at 3 things in this work: the accuracy of the directional labeling, the accuracy of the blending labeling, and a bunch of tile-based metrics to evaluate the actual content of the segments that were generated using this approach. So here we're looking at if the generated segments and rooms were open and closed in the directions as indicated by the labels used to generate them. For Zelda, this is trivial. You just check the location of the door tiles in the generated room and make sure they match up. For each of the other 3 games, we trained random forest classifiers on their training segments using the directionality labels as the class labels. So then for a generated segment, we compared the label predicted by the classifier with the one used to condition the segment's generation. Now, note that while ideally we want exact matches between predicted and conditioning labels, that is, we want the generated segment to be open and closed in the exact label specified directions, it is sufficient that the generated segment has just the desired open directions, regardless of whether the other directions are open or closed. So to illustrate that, here we have on the left an original segment of Metroid with only the left direction closed off. And so an exact match would be precisely similar to this. But when we say an admissible match, we mean something like the example in the middle, where the left direction doesn't match with the original because it's open, but it doesn't matter, right? Because the up, down, and right directions are open, similar to the original segment. But the third example, where in addition to the left, the right direction is also closed, that is not a match. And another thing to note is that because these directional labels are binary vectors of length 4, there are 2 to the 4, so 16 possible labels, but only Zelda had all 16 labels in the training set, whereas Metroid, Mega Man, and Lode Runner did not. So we separately tracked the match percentages for the in-game and the out-of-game labels because we would expect that there would be a lot higher match percentage for the labels that were in the training set versus those that weren't. So for each model, we sampled 1,000 latent vectors at random and used each of the 16 possible directional labels for conditioning, thus generating 16,000 segments. And for each segment, we applied the relevant classifier and compared the predicted label with the label used for conditioning, separately computing what percentage of in-game labels yielded exact and admissible matches and what percentage of out-of-game labels yielded these matches. And in our results, we observed that all Zelda models achieved near 100% accuracy for both exact and admissible matches, suggesting that door placement using conditioning is in fact very reliable for Zelda rooms. The next highest percentage was seen for Lode Runner. The only 4 out of the 16 labels were in-game labels, and for the remaining 12 out-game labels, the admissible match percentage was fairly low. And Metroid outperformed Mega Man in all types of matches. Overall, though, the takeaway here is that we observed about 90% admissible matches in all cases when using the in-game labels, suggesting that the models can very reliably produce openings and doors in the desired directions, even if the exact match percentages are not that high. So similarly, we wanted to evaluate the accuracy for blend labeling and again used a classifier-based evaluation method. So for each blended model, we trained a random forest classifier using the game that a training segment belonged to as the class label as described previously. So for each model, we sampled 100 latents and used each possible concatenated game and directional label to condition their generation. And for the 2-game blends, there were 2 to the 6, so 64 such labels, resulting in a total of 6,400 generated segments. And for the 3-game blend, there were 2 to the 7, so 128 labels, yielding 12,800 generated segments. And in all cases, for each possible game label, we computed the percentage of times each of the games in that blend was predicted. But what are the expectations with this type of evaluation? Well, when generating segments via conditioning with a label that only includes one of the games, we expect to see a very high percentage of predictions for that game. Whereas when generating segments via conditioning with a blended game label, we expect predictions to be more spread out across the games. So suppose we're working with the Zelda, Mega Man, Metroid blend labeled in that order. If we use 100, we would expect a high percentage of segments to be classified as Zelda, whereas if we use 011, we would expect a low percentage for Zelda, but a moderately high percentage for both Mega Man and Metroid. And there's not enough space here to show the results in detail, so for that, please consult the paper. But to summarize, the results that we obtained were in fact true to this expectation. So in all cases, when using single game blend labels, the classifier predicts the relevant game close to 100% of the time for the blends involving Zelda, at least about 92% of the time for the Metroid Mega Man blend, and about 87% of the time for the Zelda, Metroid, and Mega Man blend. And when using the blend labels, we observed more spread out predictions as we expected. Additionally, when a game's label element is set to 0, the game is usually predicted less than 1% of the time, which is also true to expectation. But the overall takeaway here is that our results suggest that conditioning can in fact successfully blend the desired games as we had intended. And for our final evaluation, we looked at the actual content of the generated segments. So for this, we used 2 tile-based metrics, namely density and symmetry. So density is the proportion of a segment or room that is occupied by walls, ground tiles, doors, platforms, and/or blocks, while symmetry, as the name suggests, is a measure of the combined vertical and horizontal symmetry of a segment or room. For evaluation for each game, we compared the mean density and symmetry averaged across the generated segments versus the mean density and symmetry for the training segments. And the results are shown in this table. So the bold values indicate generated segments that were significantly different from the training set, at least in terms of these metrics. And so we can see that the models for Metroid did the worst in capturing the original level. So this points to an area of improvement in the future. But for most of the remaining models, particularly the lower dimensional ones, no such differences were observed, thus suggesting that they did a fairly good job of capturing the content and patterns of the original games. And in the interest of time, I'll skip over 2 additional evaluations that we performed that you can find in the paper, one looking at the novelty of the generated segments, and the other evaluating the content of the blended segments in terms of distribution similarity with the segments from the original games. So I'll end by going through a few example levels generated by this approach. So first we have a generated Zelda dungeon and a generated Metroid level. The segments and rooms are highlighted using white outlines with the red dashes indicating where doors and or openings are supposed to be. And these were put together using a simple layout algorithm that is described in the paper, but really you could use any algorithm to generate a layout and then fill that in by passing the appropriate set of labels to the conditional VAE for that game. Here we have some examples from the two game blends, and as you would expect, these are a lot noisier with a lot of sections that don't look particularly playable, but I'd argue these results are still quite interesting. With some of these games, you can see they blend better than others. So some of the blended sections in the Zelda, Metroid, and the Metroid Mega Man levels look fairly smooth, whereas the Zelda and Lode Runner blend looks quite chaotic, consisting of regions that are attempting to sort of smash together the ropes and ladders of Lode Runner with the dungeons of Zelda. But in the future, you could think of the system as a whole as working with some sort of companion system that generates mechanics that render these levels playable. And in general, working on these types of approaches could move us towards building systems capable of generating entirely new types and combinations of games. And lastly, I want to talk about these examples that are from the three-game blend of Zelda, Metroid, and Mega Man, and want to highlight the fact that there are actually two broad ways of generating these blended levels. So the one on the left is generated by using the individual models for each game and having them generate segments and rooms for different parts of the layout, whereas the one on the right is generated by the actual blended model that was trained on levels from all three games taken together. And as you can probably tell, the one on the left looks a lot less noisy because it's really just segments and rooms from the individual games sort of concatenated together. And that makes for blended levels that are a lot more playable. You could certainly think of an agent that has the mechanics for all three games be able to play through these types of levels. But the blending isn't fine-grained, and there's less opportunity for finding truly novel things, whereas the approach on the right side produces these blended levels that are quite noisy and fairly unplayable, similar to some of the examples in the prior slide. But arguably, there's more of a scope for these types of models to be able to generate completely new types of levels, new types of game designs, and new types of mechanics. And so there's this little trade-off between these two approaches to blending levels. And so to conclude, we use conditional VAEs to control directionality of generated segments and rooms, which enabled us to generate whole platformer levels and dungeons, as well as blend levels across these two genres. And the main limitation of this work, as I've alluded to before, is the lack of playability evaluations. And this was confounded by a number of factors. So for Zelda, the VGLC dungeons do not contain lock and key tiles nor the Triforce, all of which are crucial for testing playability. So we just know that given how reliable the placement of doors is using the conditioning labels, combined with the layout algorithm that we use, that we can generate dungeons that are at least traversable from room to room without generating any unreachable sections or dead ends. Additionally, testing for playability of Lode Runner was hard because in addition to not having access to an agent capable of navigating ropes and performing digging actions, we work with segments of Lode Runner levels, and so we couldn't guarantee that a segment would contain the gold pieces that need to be collected in order to complete a level. And above all, blended levels would require new blended mechanics to be playable, and generating mechanics for blended games is a problem we wish to address in the future. So the next step would be to generate fully playable versions of these dungeon platformer hybrids and blends. As I mentioned before, we could take levels generated by this work and use a separate process to generate new blended mechanics to be able to play them. Alternatively, we could use an agent capable of certain mechanics and try repairing a given set of generated levels. We would also like to incorporate this work into a mixed initiative or automated design tool in the future where users can supply the labels. And lastly, although we used a bunch of different latent sizes, we didn't note much impact, both in terms of quantitative results as well as visual inspection. So in the future, we'd like to focus specifically on investigating the effect of different latent sizes on these models. And that brings me to the end of the presentation. Thank you for your attention.